So this will start the recording. Okay, so today we start the second half of 033. Very exciting, very big day for everybody. And your 6033 Engine in the News segment is brought to you by one of your classmates who posted this on Piazza, and it was like just the perfect segue. Okay, so I'm going to use this as our in the news. So this is a quote from an article just a couple of days ago, talking about an internet outage in New Hampshire and Maine. So the ISP here is Spectrum. That's what this company is, and they provide internet in New England. And they had an outage in their network, and it was a pretty big outage. And so you can see a lot of quotes in this article about, especially these days, right now, students can't go to school if your internet isn't working. We can't do our jobs, all sorts of things. But the quote that I pulled for this lecture, the reason I like this is because it's where the company is explaining what happened. And they mentioned they had two separate failures, so two separate fiber breaks. And the separate breaks have impacted our redundant path, which normally serves as a backup when a break or damage is incurred in a part of the network. All right, so you might imagine this working that, maybe the two failures, one was kind of on the primary network paths, one was on the redundant network paths, or maybe the primary just wasn't in use and both of them were on the backups. That wasn't quite clear from the article. But the reason this is such a great segue is because you can see here that this ISP tried to anticipate some failures, right? They had a primary path that their customers were using and a backup path. We talked a little bit about that in the context of BGP. We said that sometimes these days it's common to see what we call a multi-homed AS, where we buy internet from multiple ISPs and maybe use one as a primary, one as a backup. This is what MIT does on campus, right? So they tried to anticipate this failure, and yet things still broke, right? The redundancy that they had added into their network still failed, right? And so this gets us to where we're headed today. All right, where we're headed, if you recall this slide, this is the slide I ended the very first lecture on. We've talked a lot now about each of these machines individually, right? We've talked about operating systems. We've talked about some distributed systems as well that use more than one machine. We've talked a lot about the network, right? Now we are getting ready to move towards the part of the class where things start failing a lot more. All right, you've seen some examples of failures. You've seen the example that I just gave you, right, with this ISP spectrum. You've seen us think about networks and seen that there's multiple paths between a single source and a destination. Typically, in most networks, there's multiple paths. And routing protocols are built to detect failures, to be constantly updating their route so that they can route around failures. You've seen TCP, where senders are retransmitting packets in the case of loss. And then you've started to see things in bigger systems. So if you imagine DNS again, right? DNS requires that zones have at least 3 name servers, at least 3 like physically distinct authoritative name servers. So that if one goes down, you have some backups, right? So where we're going in this part of the class, we're going to start to develop sort of a more systematic way to think about failures and to deal with failures. This will all fall under the umbrella of what we often call fault tolerance. So we want our systems to keep running even when things fail. We maybe even want to recover in particular ways from these failures. And we're going to start to allow a more complicated set of failures, right? So think back to say, Katrina's amazing web suite, right? Day one, we bought a Llama, right? One type of failure that we haven't discussed is, say we're going to buy our Llama and the server that we're communicating with crashes mid-transaction, right? This is a question. Did we buy the Llama? Should we try to buy another Llama? Like, what happened? Right? We're gonna start thinking about those types of issues, right? So for the next couple of weeks, we're still imagining that things are failing essentially at random. We're not dealing with like targeted attacks, right? That's going to come later, but we're going to allow for machines to fail, disks to fail, all sorts of things to fail in our systems now, not just the network. All right, so let's get started. I'm going to start you all off with sort of a high level approach to building reliable systems. And it is so high level that it, in large part, abstracts away all of the difficulty, right? But it's going to be a nice framework for us to use in subsequent lectures. right? So here's the basic idea. The first thing we want to do is identify all possible faults, identify all possible things that could go wrong with our system, right? And sort of decide which ones we're going to handle, right? So let me just give you some examples of things that can go wrong, right? Software could crash, happens all the time, right? Zoom could crash, right? Hardware could fail, right? I'm like thinking in the context of the machines that I can see right now. So Zoom could crash my laptop. My laptop itself could fail, like the disk could fail, the CPU could fail, a fan could, something like that, right? We could see operational issues, right? Where maybe my system is fine, but my ISP has some sort of failure. Maybe that failure was caused by software or hardware, or even like human misconfiguration, right? When we talked about BGP, I told you a lot of problems with BGP are like its rules are so complex that humans often mess them up, right? We could even see environmental issues. Karen, your Zoom background is so appropriate for this moment, right? Karen is sitting with us in front of a volcano. A volcano could erupt and take out an ISP, or maybe a little bit more relevant to our lived experience, hurricanes, wind, all of these things. There are so many things that can go wrong, and they can affect our systems. So we're starting, thinking about what can go wrong, what do we want to deal with, all right? Once we've sort of gotten a handle on the type of issues we're going to try to manage, we're going to have our system have someone to detect and contain faults, right? That means that one, our system, or some module within our system, knows that a problem happened, right? In the context of TCP, that might be thinking about the sender having a timeout, right? So if it doesn't get this packet, or it doesn't receive an ACK after some timeout, it assumes a failure of a particular type and takes an action, right? Other types of detection are, maybe like a checksum on a file or something, which is kind of like a hash of a file to let us check whether a file has been corrupted, right? So you want to have a way to detect faults and also have a way to contain them, right? Containment means, limiting their propagation, right? One of the ways this comes out in a network, we didn't talk very much about this in the context of TCP, but along with TCP packets, you actually get a checksum, right? So again, sort of like a hash of the data in the packet. Switches, as the packet travels through the network, switches check the checksum and make sure that everything's still okay. If not, it means that something in the packet has gotten corrupted, and the switch will just drop the packet, right? So that packet, right, which kind of failed in some way, it's not going to go further in the network. Right, so we'll have some way to detect and contain our faults, and then we have to decide what to do, right? How are we going to handle the fault, right? Maybe even more precisely, how is a particular module within our system going to handle the fault? There are any number of options, right? And the one that you pick, it depends so much on what your system is trying to do, right? You might decide that there are some failures about which you do nothing, right? There are some failures where, a module in your system detects a failure and just immediately stops, like it shuts down. Maybe a module detects a failure and says, well, I don't know what to do about this. I'm gonna, communicate with another module. I'm gonna report this error to some other part of the system. Maybe a module detects an error and it can actually fix it, right? Or it can mask it in some way from the rest of the system, right? So again, this is super, super high level. The details are going to be different for different systems. What we're gonna work towards in lecture is actually a way to make this process not quite as overwhelming, all right? But before we begin this in earnest, I'm gonna get a few, I used to talk about these as disappointing things, getting a few disappointing things out of the way. I'm just gonna say more, let's talk about some realistic things, right? We are never, ever going to be able to get our systems to be completely free from failures. There's simply no way, right? Again, you could think about this in the context of TCP, something about which you know quite a bit. TCP adds reliability to a network. It cannot guarantee that a particular packet will get to its destination. There's always a chance that like packet number 7 could just keep getting dropped and keep getting dropped. All right. The guarantees we have with these systems will essentially be probabilistic. Right. We'll try to improve them, and I'll talk about how we assess success in this space, but we're not going to have perfect systems. Right. And spoiler for May, we're also not going to have perfect security one day. Right. Second thing, you're going to see that adding reliability to systems comes at a cost, right? There are many trade-offs that we're going to make here. Sometimes it means literal dollars. We have to buy more hardware, more computational resources, something like that, right? Sometimes it's just, it adds complexity, right? Making a system more reliable, even as much as we're trying to keep everything modular, it's going to add complexity. Again, TCP is a great kind of touchstone for you here, right? TCP adds reliability, and now there's all of this other stuff to think about. There's sequence numbers and ACKs and all of this other stuff, right? Usually the way that we approach these things is, we iterate, right? We pick a failure, we try to handle that failure, we try to see what happens, or maybe that means deploying a system, but maybe more means simulation, like thinking about things like that. So it is still an iterative process. This is still part of a design process, just like what you're doing with your design projects, right? And then the last thing I'll get out of the way before we start to talk about how do we define success here, even though software faults are certainly up for consideration here, right? If software crashes, the machine might crash, etc. We are occasionally going to rely on like some small piece of code being correct, right? As one example, the disk controller in a machine, which sort of controls reads and writes to the disk. We're going to assume, for instance, today that disk controller code is correct, right? And that might seem like a cop out, but for that type of like really, really critical code to a system, we have incredibly stringent development practices, really well-defined, really stable specifications. There's modeling, there's simulation, there's verification, there's all of this stuff, right? All of this really, really good software engineering that goes into those really, really important pieces of code, right? And there's really only a few on any particular machine. Like honestly, if Zoom crashes, who cares, right? We restart it, it's fine. If my disk controller broke, I'd be really upset, right? So we're going to try to build more reliable systems. How will we know, right? How will we know if we've made a system more reliable, right? How do we calculate this? There's a number of ways that we could think about this. In this class, we're mostly going to think about availability, right? Kind of what fraction of time is our system up and ready to be used? So really quickly, I'm going to give you an example of how we might calculate availability, because I want you to see, like, I'm going to give you this example, then I'm going to later give you an example of this coming up in the real world. We're not going to spend a ton of time on these types of calculations though, right? This isn't like, this type of arithmetic isn't going to be a big deal for us. So we're going to zoom in a little bit, right? So how do we think about this? Here is one way, all right? If you're running a system, right, any module in a system, you talk about the whole system, whatever, you can run it and you can sort of measure, okay, on average, how long does it take to fail, right? You can, and I'll adjust this, you could measure the mean time to failure. All right, so there's one thing you can measure. And again, you start the system, start a clock, measure until it fails. So you do that a couple times, you get an average, right? Once a system fails, it takes some time to fix, right? Zoom, like if my laptop crashes, it does not bounce back in like the next nanosecond, right? There is some time to repair it, right? So you can also say, okay, what's the average time it takes to repair this system, right? From these two numbers, you can add them together and you'll get something we typically call mean time between failures, right? Because again, there's sort of two states my system is in. It's working and working and working fine. It crashes and then it's repaired. It's being repaired, right? So with all of these acronyms, all right, when we talk about availability, we're just asking, right, what's fraction of the time is the system actually up? All right, so let me give you some concrete numbers. Again, I'm going to do an example in lecture because I want you to be able to put numbers to this. We're not going to be asking you to do this a ton. And write in a different color. So let's imagine that my laptop crashes once every month, right? And let's say a month is 30 days, right? So imagine 30 days, right? 30 days. Well, we'll come to this in a second. And let's say that it crashes on average, it takes 10 minutes to bring itself back up. All right, so 10 minutes, which is not true for my laptop. My laptop typically takes 45 minutes to recover from a failure for some reason, right? So I can calculate this. I can calculate mean time between failures, all right? I'm gonna convert it all to minutes for you. Again, you don't need to worry about this conversion, but 30 days is 43,200 minutes, all right? So availability, what's that like? Well, most of the time it's up, again, 30 days. But factoring in repair time gives us, decent availability, 0.9997. All right. And again, this is the first and last time we're going to do these precise calculations, although you'll see them again in just a second. All right. But why do I want you to know this? All right. Typically, a company that's running a big distributed system might have some target for availability. Right. And they will probably measure it in a little bit more of a complicated way. We'll see one example later today. It depends on the type of system. But typically, maybe they want like 99.999% availability. They want that system to be up and working 99.999% of the time. Right. This can start to give you a sense of, well, how would they measure that? Right. How would they know if the system was reliable enough? How would they know if they needed to improve things? All right. So back to our slides. Suppose, you're all system designers now. What do you do if your system isn't meeting this availability target? Like, how do you improve reliability, right? That's kind of the premise of the next 5 or 6 lectures. To improve availability, we kind of have one general technique, which is redundancy. Add redundancy into your system. And this comes about in many forms, right? Again, in the news example from earlier, having multiple paths in a network, that's this type of redundancy. Replicating critical modules in the system, right? The way that DNS has us replicate name servers within a zone, so that, again, if one fails, there's backups. Kind of tied into that is the idea of replicating data, right? Store the same data on multiple machines. That way, if one goes down, you have a backup, right? That's just a little bit more general than the name server example, right? So when you think about adding redundancy to a system, you can think about sort of the first step. Again, maybe it's you buy another network cable, you plug it in somewhere, right? You buy another machine, you buy another disk, you copy the data onto it, right? That's the first step. But then there's a lot of complexity that comes after that, right? For example, if you're storing the same piece of data on 2 machines, how do you coordinate writes? Right? You need to update that data in 2 different places. How do you make sure the write gets to both servers? Right? What happens if a write finishes on one server before the other? This is the type of stuff we're going to talk about in lectures. It's kind of all of this almost like back-end stuff that goes along and makes adding redundancy possible in big systems. What we're going to focus on in the lecture is really developing a set of abstractions that make it possible for us to get a relatively strict and pretty well-defined type of reliability. So again, we're going to start to develop abstractions that make this list on the left here more tractable, right? That help us think about well, what could go wrong and how would I detect it and how would I contain it, right? What you're going to see in recitations, you'll start to look at some systems that rest on often different assumptions than what we see in lecture. They maybe relax those constraints a little bit by making different trade-offs. Right? Maybe they want to choose performance over reliability in some cases, or maybe they're dealing with a simplified workload that means they can get out of a lot of the complexity that we are going to deal with in lecture, right? Again, another example that you've already seen. When you think about DNS, caches all over the network, right? That a particular name to IP address binding can be in a bunch of different places, right? With the authoritative server, if it needs to update that binding, it doesn't try to communicate with everywhere in the network that has a cache. It just says, well, I've made this update. There might be some stale data out there. and we're just going to roll with it, right? Eventually those cache entries expire. Everybody will get the correct data eventually, right? If I want to have it faster, so my cache expiration times be shorter, but just going to deal with that fact. All right. So today, what we're going to talk about in earnest, I mean, I've been talking to you for a lot already, right? What we're really going to talk about today, we're going to think about disk failures, right? Which means that today we are living in a world of just one machine, right? The reason we're living in this world today is because if your disk fails, things can go really, really wrong, right? If your disk fails and you lose data, it's going to be hard to recover from that, right? So we want to try to, we really don't want to lose data, right? And then also in some sense, we want to make an individual machine as reliable as possible. It's not going to be perfectly reliable, but that way we're starting with a good basis to build these bigger systems. Additionally, this is going to be a very cool application of replication, which was a lot of fun for me to say. I wasn't expecting that. What a joy. All right, so why talk about disks, right? Why talk about disks instead of another part of a machine? Again, unlike other components on your laptop, the disk is one where if it fails, things are really bad, right? If your CPU fails, fine, go out, buy another CPU, you're good. If a fan fails, go out and buy another fan, right? If Zoom crashes, restart Zoom, right? If the disk fails, you can't just go out and buy a new disk and swap it in, right? All of your data is gone, right? You really want that data to stay. And disks can fail in any number of ways. You see the whole disk stop working. You might see, especially in, like magnetic drives, maybe just a single sector of the disk fails, right? So there's all sorts of things that go wrong. So an interesting question, it would be, how common is this? Does this happen that much? So I bring to you today some specs from a recent disk made by Seagate. And I bring them to you in part because they use a thing that I just taught you about, right? So they point out mean time between failures. We just did that, right? It's real, it's in specs, and you can see that in this disk, it's 1.2 million hours, which seems suspicious. I didn't do this math beforehand. I would guess that's like 140-ish years. Somebody can put it in the chat, but it's a very long time. We haven't had disks for this long. It's really quite long, right? So what's going on here? Did I teach you a metric that is useless? Not quite. You can also see that they've reported this other quantity, 137 years. I said 140. Oh, nailed it, right? They've also reported this annualized failure rate. And this is a quantity that's specific to disks. And here's what it's capturing, right? Disks don't fail uniformly. If you buy a disk, it is most likely to fail very early, like early in its lifespan. I don't love the word lifespan here, but you get what I'm saying. Very early in its lifespan, or after maybe like 5 years, right? So like failure probability would be sort of high, and then it would go shoo, and then it would start to grow again over time. All right. Mean time between failures, it does not capture that. All right. Mean time between failures is thinking about, things are failing uniformly at random. Probably they got that number by, say, putting a bunch of disks in a warehouse, let's say like 1,000 disks, running them for a pretty decently long time, 100 to 150 days, something like that. And then said, okay, well, some fraction failed. We can extract the mean time between failures from that. All right, now that's one way to do it. But this other quantity, annualized failure rate, never going to ask you to calculate it. You can look it up on Wikipedia if you really want to calculate it. It takes the mean time between failures and then factors in that distribution that I talked about, where it's more likely for disks to fail early or after a couple of years, but kind of not in the middle. All right. So, well, this is just one example of, specific systems will measure success in specific ways, but looking at things like mean time between failure, things like that, that's a good starting point, right? Now, what do you do with this knowledge, right? Here you see an annualized failure rate of 0.73%. That's less than 1%. That doesn't seem bad, right? This is saying the probability of a particular disk failing within a year is less than 1%, right? But now imagine, again, as always, we are running Katrina's Amazing Web Suite. Katrina's Amazing Web Suite is going to need more than one disk. So many servers, right? Surely at least one of those disks is going to fail, right? This is why we are studying reliability in the context of large systems. Even if the probability of like this specific disk failing is low, the probability of some disk failing in my big system is high, all right? So again, we're gonna imagine, even though different parts of a disk can fail, we're gonna imagine a whole disk failing. That's the failure we're thinking about today. That's the failure that I have identified to you. So how are we going to fix this? All right, with a blank slide. All right, so let's start. We're going to go through a number of techniques, 3 techniques today. They're all part of a suite of techniques known as RAID. But I'm going to start you off with an idea that I've already mentioned in this lecture. All right, so here's our disk. All right, that's disk number 1. It's got some data on it. We'll do yellow. All right, so there's the data. First idea, I'm worried about this disk failing. I'm worried about losing some data. I'm gonna buy a second disk. And I'm gonna copy the data to the second disk, right? And again, we're thinking about disks here. So you're imagining like this is happening, on one machine, right? So one machine is now communicating with 2 disks, all right? Thinking about some logistics, a few things get a little bit more complicated, right? If I need to do a write, right? I have to write a piece of data. Okay, I need to write it to both disks. It's a bit more complicated, but our disk controller, they can issue that in parallel, right? Might slow things down a little bit because we want to make sure both writes succeed, but this is okay. Again, it's on a single machine, right? Imagine one machine. We don't have a network involved yet. I'll label this so that you know what this box is. All right, we don't have a network yet. If I want to do a read, that's actually kind of cool. I could do a read from disk 2, or from disk 1, right? I could read from both. That's fun, right? Now, how would I detect a failure, right? Suppose that disk 1 fails, right? We're gonna assume that the disk controller can detect that. That's part of its job. We're gonna assume that code is correct and is working, all right? But so disk 1 has failed, right? What do we have now? We still have all of the data, right? We can still read the data. We can still write the data onto disk 2. One hopes that eventually we will buy a new disk, right? We'll plug it in, we'll replace disk 1, we'll copy all of the data over, all right? This is great. This is great. We can handle a single disk failing, right? As long as both of these disks don't fail at the same time, we are good to go, all right? The thing that the trade-off here is, well, okay, writes are a little bit slower. There's a little bit additional complexity, but there's going to be one kind of worse trade-off, which I'll illustrate to you in a second. All right, so what I just described to you, it's known as RAID 1. Right, RAID stands for Redundant Array of Independent Disks. I'll put it in the chat so you don't forget. All right, redundant array of independent disks. There are multiple levels of RAID. This is RAID 1. So RAID 1 it refers to mirroring data. All right. If you had 2 disks worth of data, say a yellow disk and a blue disk, right, you would buy 2 additional disks and mirror both the yellow disk and the blue disk, right? And you could also extend this idea, right? If I wanted to be able to handle 2 disks failing at once, I could copy things onto a 3rd disk, right? I could add disks here. And so again, that we can recover from a single disk failure. That's kind of what we wanted. But I have to buy twice as many disks, right? To get this to work, I went out, I bought a whole new disk. I did not get any additional storage. I just copied all of my data, right? And again, if I had n disks of unique data, I'm going to buy n more disks, right? And mirror all of them, right? This is the main drawback in this case. That is a lot. That's a lot of disks. So we're going to be smarter about this. Virtually every other level of RAID is smart. This is sort of the baseline case, which is still good. It's simple. That's nice. but you have to buy so many more disks, right? Now, here is the basic idea. I will bring this picture back up for you. This picture will not be leaving your side, although it is leaving your side right now. It's going to return to you, right? So let's do some more drawings. We're going to exploit a particular principle, and this might surprise you that it's coming up in 033. All right, we're going to talk about bits and truth tables for a second. All right, suppose we have two bits, A and B. They can take a variety of values. They could both be 0. One of them could be 1. They could both be 1. There are 4 possible combinations here. And, you do lots of fun things with bits. The most fun you can have is by XORing them. All right, so XOR is true if exactly one of the inputs is true. Right? If it's been a while since you've XORed some things, you're fine. Now you know how to do it, right? So here's a nice thing. If I give you a bit A and a bit B, you could calculate this bit C. You XOR them together, you're good to go, right? But notice what else you can do. If I gave you, and I said, hey, here's A, but then here's C, and I asked you to tell me what B was, you can also do that, right? And in fact, the way that you get this, you just XOR A and C together, right? So you've noticed 0 XOR to 0 is 0, 0 and 1 is 1, 1 and 1 is 0, 1 and 0 is 1. Similarly, if I gave you B and C, you XOR them together and you get A, right? You could extend this idea. Why stop at 1 bit or 2 bits? Why not have some strings, right? Why not say, well, here's my collection of bits, right? These are 2-bit strings. You can XOR them together. If I move my paper up a little bit, right? Right. When we XOR bit strings together, we just do them position by position, right? So 0 XORed with 1. I didn't mean to make these all work out to 1, but here we are, right? And you have the same thing. If I give you A and B, you could calculate C. That's what we just did. If I give you A and C, you can calculate B. Again, you'd XOR them together, right? If I gave you B and C, you could calculate A. We're going to extend this idea to disks, because all a disk is a really long bit string. That's it. It's just got a bunch of bits. All right, so here's the approach. Here's the first approach. We're going to take, I'll do 3 in this example. Right, we have 3 disks here. All right, and this time, I'm going to start by having the disks all have unique data on them, right? And I'm going to do them kind of in lines because I want you to think of them as like sectors or chunks of data, right? So I've given 3 sectors, a very small disk, but 3 sectors there. Disk 2 has its data, right? Disk 3 has its data, right? There's our disks, right? Now, if we were doing mirroring, okay, we'd buy like disk 4, disk 5, and disk 6, and we'd mirror them all. Instead, we're going to buy 1 additional disk. And we're going to call it disk P. P is going to stand for parity. All right. What we're going to put on disk P is, okay, sector 1 of disk P is going to be the XORs of all of the other sector 1s. All right, and I'll put some words to this on the slide in a second. Sector 2 of disk P is the XORs of all of the sector 2s, sector 3, etc. Right, so just so you have it here. Sector 1s, or sectors 1, like attorneys general, right? This is, I don't know, I like this so much. I think this is so clever. So we're going to talk about this in a little bit more detail in a second, but let's just think of what's going to happen in a failure. All right. Suppose that disk 3 fails. We can still figure out what was stored on disk 3. All right. If we XOR all of those first sectors together, we'll get the first sector of disk 3. We XOR all of these second sectors together, we'll get the second sector of disk 3, etc. Right? Another way to think about this is that I have like these 3 inputs, and then this disk is like a function of those 3 inputs. Right? If I'm missing one of the inputs, but I have the output of the function, I can still get that input back because of the beauty of XOR. All right. And similarly, you know, if we eventually buy a new disk, come in, swap it in, plug it in, we can rebuild disk 3. All right. This is very cool. All right. So again, this picture, I'll bring it back for you in a little bit of a nicer drawing. All right. This is known as RAID 4. What happens with 2 concurrent failures of disks? We're not there yet. We're not there yet. We're only going to have 1 disk fail for the moment. All right. So RAID 4 has a dedicated parity disk. All right. And notice that, you know, RAID 4 is actually useful even if just one sector of data was failing on a disk. We could reconstruct it in some way. So it's kind of nice for that as well. All right. What are RAIDs 2 and 3? Y'all are anticipating the lecture very well. I'll talk about RAIDs 2 and 3. Good catch that we didn't do them. We'll also talk about multiple disk failures. I love it. I love the questions in the chat. You all know what's coming. All right. So what happens? Oh, what happens if the parity disk fails? Hey, that's a great question for right now. Let me bring my picture back real quick so I can point to you. This disk, despite having a special name, is in reality no more important than any other disk, right? Modulo is something we're going to talk about in a second. If, imagine this is not dead, but this is really dead, right? The parity disk is gone, but I have disk 1, disk 2, and disk 3. Again, you're imagining that this is not X'd out, right? I can buy a new disk and reconstruct the parity. I don't actually need the parity disk to read any of the data, right? This is a great question because there is the sense that the parity disk, it's special in some way. Not really, right? Like when we did this truth table, A XOR B isn't really any more important than A or B, right? But we will talk about the parity disk in a second. So I love this question. I love all of the questions, right? So what happens? Well, you know, what do we get from this? We get some good things. We can still recover from a single disk failure because we've not made it to 2 disks failing at once, right? We only have to buy 1 extra disk, right? In contrast to mirroring where we were buying twice as many disks, right? Now, one other benefit I wanna bring up here, and this relates to why we didn't cover RAID 2 or 3. We even can, in a system like this, where we have multiple disks storing, you know, multiple copies of data, there's not multiple copies of data, storing different data, we can get a performance benefit in a particular way. Imagine you have a really, really big file, right? So I'm storing a really big file. You need to read it, right? If I put it all on 1 disk, you're just going to do a really long sequential read from that disk. If I stripe it across multiple disks, I say put 1/3 on this disk, 1/3 on this disk, and 1/3 on this disk. You could issue some reads in parallel and get the whole file through those parallel reads. This really has nothing to do with RAID, right? This is just a performance benefit that you can get once you allow your system, your machine, to have multiple disks, right? But the reason I bring it up here, and the reason it relates to RAIDs 2 and 3, if you take a look at the original RAID paper, sometimes we read it in O33, often we don't. It talks a lot about reliability, but it also talks a lot about performance, right? It's this really interesting presentation of all of this idea. And those types of performance benefits came up a lot in the discussion of RAID. And in particular, the reason we're skipping RAIDs 2 and 3 is because they do writes a little bit differently. They provide you no additional reliability and they perform worse than RAID 4. Like there is no good reason to use RAIDs 2 and 3. When I read, like if I'm reading the original RAID paper, like in my leisure time, I typically think of RAIDs 2 and 3 as being more like pedagogical tools to get you to RAID 4. We don't really see them very much in practice, if at all. All right. Now, as you can see, there's still room on the slide. This is not our final thing, right? So I want to think about, you know, what is a big drawback with this? So I'm going to ask you, I have a poll, and I'll say the poll out loud so that the people who are the people who might be watching later, right? So here's the setup in the poll, which is anonymous, right? Imagine this RAID 4 scheme. Imagine 3 data disks and 1 parity disk. All the data disks, they have different data, right? So we've got 3 disks worth of data. We're gonna do a bunch of random writes, all right? A bunch of random writes. Which disk would get written to the most? Like which disk is gonna experience the most updates from writes? While you all think about that, I'll talk about this this question about the performance benefits of RAID 4. And so again, this doesn't really come from the style of redundancy we're seeing in RAID. This is really just something you can do when you have multiple disks, right? So if I have 3 disks and I want to store a really, really big file, right? If I put 1/3 of the file on disk 1, 1/3 on disk 2, 1/3 on disk 3, right? I could do a reads in parallel, right? I can read all parts of the data at once, get the data faster. And again, I'm assuming like I'm kind of on the same machine. There's not a network to worry about, right? Versus if I just store the data on contiguously on one disk, I'm gonna have to read through the whole thing. I can't do anything in parallel. All right. So many of you have voted, and many of you, not all of you, which is totally fine. Many of you said, hey, this parity disk, right? It's gonna get a lot of writes. That is a downside here. All of the writes have to go to the parity disk, right? It seems sort of inevitable at this point that we're going to have to write data to 2 different places when we're adding redundancy. That's okay. We're sort of willing to accept this. This parity disk is going to start to be a bottleneck. All right. It's going to wear out faster. It's going to, again, it's going to be a bottleneck for those writes. So let's fix that. All right. So again, this slide will come back for you. All right. Here's how we're going to fix it. I've prepared a demonstration. All right. That's our previous one. All right. So here we are again. This is RAID 4, just with Post-it notes, which I was excited to use. All right. This is what RAID 4 looks like. Okay. Disk 1, I've got 4 sectors of data now because I had room for that. Disk 2, disk 3. And then our parity disk, I just call them A, B, C, and D. All right. So the problem here, if I do a write, right, if I update, say, sector 4 on disk A, I also need to update this, right? I need to update this XOR value, right? And if I write to sector 2 on disk B, I need to update this XOR value. So I'm updating the XORs all the time. There is no reason that these XORs need to all be stored on the same disk, right? Again, this parity block, these parity blocks, parity sectors, whatever you'd like to call them, they're really no more important than any other sector. They don't all need to be on one disk. There's nothing special about disk D. Move them around, all right? I'm going to do them in a disorganized fashion, right? But like I could just say, okay, that XOR goes here. This is why we use Post-it notes, so I could easily move them. Unfortunately for you, you all don't get the joy of moving these Post-it notes around. I'm having a great time, right? But look at that. We can spread these XORs around, right? And again, you might say, well, okay, things got a little bit disorganized. Well, we can clean things up. We can make sure that we have sort of orange, pink, and blue all the way across each of these things, right? So we have to do a little bit of work in organizing. But now, all right, if I want to update, a sector 1 anywhere, I write to its disk and to that XOR, which is on disk A. If I want to update a sector 2 anywhere, I write to that disk and this XOR, which is on B. All right, this is RAID 5. All right, so here's RAID 5. Spread out the parity. All right, this gets us out of the main drawback of RAID 4, which is that particular piece of hardware got so many different writes. Right now, RAID 5. RAID 5 is, of these 3, the one to use. Right, it's sort of I always hesitate to make like very strong claims like this. It's objectively better than everything else on this slide. We also see RAID 6 in use today. RAID 6 works on the same principles. It works on a different type of error correcting code that's fancier than XORs. It allows you to recover from 2 disks failing at once. Right? How do you keep track of what information is on what disk? You would have a disk controller that would be doing that mapping. All right, so you would be able to keep track of this. You are right to point out, though, that like there is a little bit of complexity involved here. Right? We have to keep stuff more organized now. Right? But your machine can keep track of what data is stored where. It can also keep track of how the XORs are spread out about here. Because remember, these are all disks. They're in the same machine, etc. Right? So this is what we're going to do with RAID. Again, RAID 6 lets you recover from multiple disk failures, from 2 disk failures at once. It's pretty cool. We just don't have a chance to get into it in O33. We don't quite have the background for that. But what has this given you now, right? How are you going to use this in the rest of O33/your lives, right? Our goal here, our overarching goal, is to build reliable systems from unreliable components, right? And we want to eventually build really big systems. Today, I sort of kept you on one machine, right? RAID is going to let us recover from single disk failures on one machine or multiple disk failures if we just extend those ideas out a little bit. And what this is going to help us do is, be reasonably confident that if a machine crashes, we're not going to lose data, right? There's a complicated issue about what should happen, say, if a disk crashes mid-write. That's something we'll think about on Monday, but modulo that, we're going to be pretty confident that we're not losing data, right? We made some trade-offs. We had to buy more hardware. Reads and writes and general data organization, just like Savannah asked in the chat, they've got a little bit more complicated, right? In some places, we even saw some performance gains, right? Thanks to parallelism. So tomorrow in recitation, you're going to look at a system called GFS, a Google file system. GFS takes a piece of data and stores it across multiple machines, right? Not just multiple disks in one machine, but multiple machines. And on the surface, it might not seem clear how that relates to what we're doing in lecture right now, how it relates to RAID. Again, think about it as a system to replicate data across machines. And think about that in contrast to RAID, right? GFS is going to have to face problems that RAID doesn't. There's a network involved, right? There's going to be multiple users involved. You only have so much to talk about, right? And you could certainly think about, would RAID work in that environment, right? So that's how this connects to tomorrow's recitation. But let me tell you where you're going in lecture, right? One of the things that makes GFS work, which you'll discuss tomorrow in recitation, is that it makes some simplifying assumptions about the type of data that it's working with and how that data is accessed by users. In lectures, we're going to try as much as we can to not rely on those types of simplifying assumptions, right? In lecture, we're thinking about big systems accessed by lots of people with lots of servers in lots of different ways, right? One of the things that's going to make this process tricky is having to think about all of the possible ways that our system can fail. The example I started you out with, buying a llama, right? The server crashes as we're buying the llama. What happened, right? That machine crash could have happened at any line in the llama buying code. How do we reason about this, right? Like, how does our system sort of clean things up and, decide whether it should charge our credit card, or like, how do we know that we bought the llama? All of these things, right? In the next lecture, we're going to go into a similar example in a lot more detail. We're going to start talking about some abstractions that will make these failures easier to reason about. And just so I can give them a name, the abstractions we're going to talk about are atomicity and isolation, right? We're going to keep those abstractions around for the entire time, the entire 5 or 6 lectures. And we're going to work on supporting those 2 abstractions, atomicity and isolation. Again, you don't know what they are yet necessarily. We're going to work on supporting them in bigger and bigger systems, all while also caring about performance. All right, so this slide, I'm going to start and end on this slide in every lecture, so you can see the you'll see the system in the top right kind of grow. This slide will get a little bit more involved, right? The final thing that I want to leave you with, right? The thing that I want you to start thinking about in the back of your mind. These systems back real things that you really use, right? They back your bank account. They back Zoom, right? They back your email, all of these things. Outages in these systems affect real people in tangible ways, right? That is what the news item from the top of lecture illustrated. So how you choose to handle failures in a system, it matters, right? It matters to real people that there are particular types of robustness here, right? So this part of the class can get it seems a little bit like in the weeds. We're going to do some very detailed stuff. I want you to constantly be connecting that back, and I will, of course, try to help with that as much as I can. Connecting that back to real systems that you really use and understanding that failures have a huge impact on people's lives, right? And so we're going to try to have things fail as little as possible, right? So that is the end of the first lecture in failures. I'll stop sharing and I will stop recording.